Don't turn in 3-4 if you haven't already turned it in, okay? So 3-6 is tessellations. Need you guys to go through and answer those questions there. Tessellation is going to be fun. We get to do our tessellation project. If you look over at the wall, you can build your tessellation project later. But we got to get going through the notes first, so start. Okay, well, let's see how we did here. First of all, what's a tessellation? Go for it, Cameron.
Reading pattern of figures that completely covers a plane without gaps or overlaps.
All right. Very good. So when something completely covers a plane without a gap or overlap, it's a tessellation. So when we had those figures on the wall over there, or if you think of like maybe at home, if you have tile on your floor, that's something that's tessellating. Now it may be multiple figures if it's tile, okay, but we want to just take into account some of the shapes we know here. So on this sheet, you went through and you figured out which of these items, if it's a regular polygon, which one's tessellated. All right? So first, what's the sum of all the angles of a square? 360. Okay? How about a pentagon? 540. Hexagon? 720. Septagon? 900. Octagon? 1080. Okay? Entagon? 1260. How are we getting this, by the way? Good. So this was, remember, this is our n minus 2 times 180. Remember, that's how you find the sum of the interior angles of a regular polygon, or of a polygon. Okay? So in this case, they're regular, so that helps out. How about decagon? 1440. Hentagon? 1620. And dodecagon? 1800. So now the measure of one of those angles of that regular polygon, what do we have to do with this? Go ahead, Cameron.
Take that and divide it by the number of sides or angles.
Good. I don't know how to turn that off, I guess. Take that and divide it by the number of sides or angles. So in this case, I'm going to take my n minus 2 times 180. Unbelievable. And divide it by...
Take the batteries out.
Yeah. No, don't worry about it. Divide it by what? Divide it by n. Okay, so 360 divided by, this is our n. 360 divided by 4 is? 90 divided by 5? 108. Divided by 6? 120. Okay, divided by 7? 128 what? Yeah, 128.6. Okay, it kind of goes on. I think it's 5.7, blah, blah, blah. Okay, 8? 135. 9? 140. 10? 144. 11? Point 3. It keeps going on, right? Doesn't end. How about 12? 150. So the question is, does it tessellate? Well, this one did. The triangle did. How about the square?
Yes.
How do we know if it tessellates? Bethany?
If it's 6 or less side angles, yeah.
So 5 will tessellate?
Yeah.
Okay. I don't think that's quite right. Go ahead, Maddie.
The sides can all be even numbers.
No, not quite right. Think about when you're tessellating. If I have, say, a triangle, when my 3 angles come together, in order to tessellate, we have to be able to make it so that these angles, as they, and let's actually just draw the angle in there. Okay, if I'm trying to get all the angles to add up to 360 degrees, as I'm coming in here, what do all the interior angles have to form? I got 1, 2, 3, 4, 5, 6. Okay? each one of those is 60 degrees. Okay, 6 goes into 360, or 60 goes into 360 6 times. So in order for it to work out, for a regular polygon to work out, these angles that are in here have to fit into 1 or 360 evenly. Okay, so 60 goes into 360 evenly, as does 90. Right? If I'm drawing a square, I can put 4 squares together. Kind of crude squares, but notice them where they come together. These 90-degree angles make a circle. Right? Will 108 make a circle? Carson?
Well, so does that mean that all interior angles have to be congruent?
They are all congruent, right? 108. I mean, we got 5 congruent angles here. They'll each be 108, but the question is, will they match up evenly? So, like, let me do a different picture. So, taking a look at this. Notice when I put these 60-degree angles together, they make a circle. They tessellate. These 90-degree angles right here, they make a circle. They tessellate. 108, well, I get 108, and I get 108. Well, I can't fit. I'd have to use a part of each. I'd have to use a part of one or a whole one and a part of another to make it fit. 108 doesn't go into 360 evenly. Yeah?
So to get that, would you do 360 divided by that angle?
Yeah, you'd have to do 360 divided by whatever this angle is. And if you get an even number, then it works out. So if I took 360 and I divided it by whatever, if we wanted to call this A, divide that by A, and if it equals an even number,
They have to be even?
or if it equals a whole number, okay? Maybe not even, a whole number. Even number is a poor term there. If it equals a whole number, you're good. All right? My paper got all wrinkled there. So 540 divided by 108, does that equal a whole number? No. How about 120?
Yes.
Yeah. Well, this isn't even a whole number, so this isn't going to work out. 135?
Anything above 6 is no.
Yeah, anything above 6 is going to be a no. Do you know why? Just is? Who just said that?
I said it, and you said I was wrong, and I don't like that.
Okay.
Because all the interior angles would be too large.
Okay. So you just said that?
I said if it's 6 or less, then it works, but
But
it's not.
But-
But it's not all
but-
60.
Okay,
but that's not true, right?
okay. Okay, but you can't go past 6, is what I'm saying.
Okay, well, if you're going to get offended by that, then what you have to be able to do is take what you say and make it an actual true statement. Otherwise, you can't get offended. Okay? All right. So number 3, explain why no regular polygons with more than 6 sides tessellate. That was the question there. Does anyone know that? So we're focusing in on these things right here. Why would those never tessellate? Talk with your neighbor about it there. See if we can figure it out.
Emma. Like, wait, no.
Go for it, Emma. Try it.
But I think it's because 120 goes perfectly into 360 3 times, but after that, none of the numbers will ever go into 360 perfectly.
Good,
Because-
yeah. That's it, yeah. 120 will go in 3 times, right? That's this one right here. It goes in 3 times. So 360 divided by 120 is 3. The next perfect number that will go in is 180. But we don't have a figure that has 180 degrees in it. Okay? Per angle. So none of these will go in equally. Or Julian, what'd you say? Yeah, you can't multiply any of these by a whole number to get 360. That's another way to think about it. All right. Very good. Theorem 3.5 and 3.6, every triangle tessellates, every quadrilateral tessellates. I want you to write down why that is. All right. Yep, so every triangle tessellates because 60 goes into 360 evenly. Every quadrilateral tessellates because 90 goes into 360 evenly. However, this isn't saying every right or every regular triangle and every regular quadrilateral. Okay, so why does every triangle tessellate? Cameron thinks he knows. Logan, what do you think?
Okay, because like the triangle, like you can put every angle together and make like a certain shape, except for maybe right triangles.
You're close. You have to put every angle together. Bethany?
But no matter what, they're gonna add up to 360.
It's true. So you guys put yours two together, and that kind of works. So if you have every angle being put together of a triangle, how many degrees do you get? You get 180. Right? So no matter what, if you have a triangle, if you cut off the three angles and put them in a straight line, you get 180 degrees. Okay? Always. So how many triangles would you need? Well, you need at least two, or at least the angles of two triangles, right? Okay? To get it to tessellate. And a quadrilateral, what does it always add up to?
360.
360. So Cameron, what are you going to say there?
I was gonna say basically the same thing you did.
Okay, same thing, yeah. So no matter, you can draw the goofiest looking quadrilateral you've ever seen. Okay? This angle plus that angle plus that angle plus that angle. You can piece them together to form a circle. Okay? It'll tessellate. So if you took a quadrilateral that was like this and you cut out 20 of these shapes, you can puzzle them together to make it tessellate. Okay? Because all quadrilaterals, all angles add up to 360 degrees. Now these aren't, I guess, accurate markings if we're thinking mathematically, but all right. Very good. Logan.
I think I have a question about the quadrilateral thing. Do they all have to be the same, like the same shape quadrilaterals?
If they're going to tessellate, yeah.
Oh, okay.
Yep.
And it could be like the weirdest shape quadrilateral ever, and it could still tessellate.
It's still tessellate, yep.
Have like an indent somewhere and it'll still tessellate.
You guys are going to have a chance to test this out tomorrow.
Okay.
Okay? That's when we're going to do our tessellation project. All right? So right now, take a look at your assignment. We're on this. Some of us, I've noticed it more.
14, does that have, you have to like fill up a whole page of graph paper?
Good question. So let's start with number one. It says, describe the symmetry of each tessellation. Copy a portion of the tessellation and draw any centers of rotation or centers of rotational symmetry or line symmetry. Okay, so if you're doing this, you would have to, here's the shape that's being tessellated. You'd have to identify the shape first. So here's my shape that's being tessellated. So you'd have to copy that shape off into a piece of paper and then show where it's tessellating from. So like how is it tessellating because they are able to, well, in this case, they're just asking you to list the rotational symmetry. So there's a point of rotation right there. Okay, the centers of rotation would be right in the middle. It spins. How much does it spin? Looks like 90 degrees on it, yeah. So it spins right there. I don't even think it's asking you to tell what degrees. So just show where the rotational symmetry is and then show the lines of symmetry. So does this one have line symmetry? No line symmetry on it. So you just need to draw your
I
rotational.
don't think it's 90. If you look closely, one of them's sharp and then one of them's more rounded.
Yeah, I think it's just gliding.
Is it not 90?
Yeah, it's not
That one looks,
rotating, it's moving.
Yeah.
that one.
They just fit together.
It's like 360 when rotated.
No, it's
It looks like we've got that piece.
That is bigger than that top one.
Yeah, that does look like, yeah. Does it go 180?
yes.
Really? Because it's still on the
looks like a point right there. More of a point than that one. Yeah, it looks like this one's just sliding. Doesn't look like there is any, doesn't look like we have any rotational or symmetry. You just copy the piece that's translating there. Okay, so just say, yeah, just copy this down. No point in this. This is just translational. Okay, they're just sliding it. But this one right here, this one has line symmetry, right? Yeah, so this has line symmetry right there, if you're looking at the shape. Yeah?
Wait, do you want us to like copy the whole shape, or can we just outline it on the thing? As long as we know what shape it is.
You can just copy this shape right here.
So just outline it?
Yeah.
By copy, do you mean?
Yeah, you can just outline it. That's fine. You can just outline it. Okay, and we have our line symmetry right there. I think with its point symmetry, with its rotational, they're actually asking you to try something differently than what I'm asking. But I would rather, for now, what I want you to see is see the shape that's tessellating, and then label any.
Keep it.